So the first step in this project, which is determining the parameters for a not well mixed or separately well mixed tank. So first we can assume that there's constant fluid properties, constant UA, and no dynamics of our controller gain. So the first step in this process is to determine the mass balances and energy balances just to simplify the system. So the mass balances simplify the system by relating the Q's. So we have QR in the middle is related, and then the Q in equals Q out, so Q is Q. Then we can find the dynamic energy balances to determine how our temperatures relate. So here we have rho v and C is constant, which was assumed above, and we use the mass balances to further simplify this equation, getting this for tank 1 and this for tank 2, which is just basic algebra. We do have in minus out plus generation. This is generation, we're adding heat. And this is not steady state, so we have to apply our derivative over there, although we can pull out for constants. Then once we have our energy balances, you take the transfer functions to determine you linearize it to get the transfer functions to determine how T1, the temperatures relate to each other. So for our first tank, we just linearize our energy balance after taking the Laplace transform here and linearize, and then we do the same for tank 2, slightly different numbers. We can also figure out that tau 2 is equal to this portion, and then our other process variables are equal to different portions. Same with above up here. And this is just to simplify, you write it in standard form to get these K's. Next, we want to write our block diagram. So this is our controller in. We're not worrying about the valve yet, and this is our process over here. So we can simplify this using the loop law. So this top one up there, these two get simplified to this, and then we just keep our top value there. Then we want our overall transfer function of our process. So we can again simplify. They add together here. And then you get, after doing some algebra, refitting to the standard model, we get this here, and then where this is equal to things that we solved for earlier. Next, we want the overall process block diagram, which we just got, and then we can write that in here and here for that simplified version. So next, we're going to take our controller offline and determine how concentration affects T1. So we can see from the process diagram, this goes away when we're taken offline. So you just get GV times GP. This is GP, this is GV. Multiply that out. Then we want to do Heaviside expansion for partial fraction expansion. In order to simplify this, we can take the Laplace transform. So first, set S is equal to negative 1 over tau V, and then multiply by tau V S plus 1. So you get alpha 1 is equal to this guy. S is equal to 0, you just get alpha 1 plus alpha 3 equals kV ks prime. And we get this mess for alpha 2 after setting S equal to 1. And then I'm just going to leave the alphas there because we can calculate and back solve for them later. So this problem, Laplace transforming, we can then Laplace transform our function after we get our alphas, and using the standard equations, we get this value, these values here. Next, we want to determine, or we want to use this and fit the data in Excel. So use your equation plus the steady state value to fit that in Excel. And then you can determine what those values are based on the equations that I said before. Type basically everything in. Then we're going to extrapolate our design conditions. So running back to the steady state energy balances, we can solve for TS and T2. Plug in the values that we got from Excel. We get 144 and 14.1 respectively. Next, controller tuning. So this is our standard form of the equation. And from our experimental data, we get these values. You can then plug those into our Ziegler-Nichols heuristics and get these values. Then using Simulink, we plug in all of our transfer function gains and time constants, and we get a maximum change of 2, which is degrees C, for a step change of 10.